Srijeet, will you start now?
Okay, thank you. Good evening, everybody. This is the third math club talk of ISI Kolkata this semester, and the title today is Probabilistic Number Theory and the Values of Riemann Zeta Function. So, is my screen visible?
Yes, it is.
Okay, thank you. So, let us start with an example first. Uh, so, suppose someone asks the question that what is the probability that a natural number chosen randomly is divisible by 7? Now, somebody might be compelled by his or her intuition to think that the answer is 1 by 7 because there are roughly 1 by 7 numbers which are divisible by 7. But there is another person who says that you cannot choose a natural number uniformly at random because natural numbers is an infinite set. So, what do you mean by choosing randomly? The question is therefore not a very precise mathematical question. So to formalize the where is the problem? So when we are choosing the natural numbers, then my probability space is the space of natural numbers, and since this is an countable set, the sigma algebra can be taken to be the power set of the natural numbers. But with this as my sigma algebra, there cannot be any measure which like any probability measure which gives equal probability to all the natural numbers because this is an infinite set. But still, is there some mathematical way to justify the first person? So the problem was that natural numbers was an infinite set. So we can take this set, which is omega capital N, then natural numbers 1 2 up to n, and this is a finite set, so that is also a countable set, not countably infinite but still countable. So we can still work with the sigma algebra, which is the power set of omega n, and this measure, which is just the cardinality divided by capital N, this gives like a uniform probability to each of the natural numbers. Now we have our random variable capital Xn, which sends n to 1 or 0, like an indicator that n is divisible by 7 or not. Now this capital Xn, if I vary my capital N, the random variable changes, and since my probability space is changing with the it's changing as the sequence proceeds, the only mode of convergence to talk about is the convergence in distribution. So we can see that Xn actually converges in distribution to Bernoulli 1 by 7. So this is a matter of just calculation, because if you look up to finitely many n, then roughly 1 by 7 of them would be divisible by 7, and there would be a small big O of 1 by n error term that will go to 0 as n goes to infinity. So ultimately this random variable will converge to Bernoulli 1 by 7, and that is possibly one way to justify person one's claim that the probability is 1 by 7, although it is not really a probability in that sense, but you can think of it. And this statement can be a formal mathematical statement, and it is a formal mathematical statement. So some other similar examples. So we are working with the previous probability space, and now let's say we fix some q natural number and consider the reduction modulo q. So this is pi qn is just the remainder after division by q. Now this capital Xn, this will converge in distribution, as you can expect very much, to uniform probability on Z mod Qz, which makes sense because if I look modulo Q, then all the residue classes will have equal weightage. And there is not really any necessary to take one modulus Q. You can take some finite set of co-prime integers, let's say Q1 up to something, and consider reduction modulo all of them. Then this random variable Xn will converge in distribution to X, which follows uniform over this product Q belongs to X, Z mod Qz. So if there are more than one modulus to which we are taking the reduction, then the remainders are getting independently distributed, and all the remainders are uniformly distributed. So this independence is actually the result of Chinese remainder theorem. If you just count it, you can see. There are also other examples that this Bn represents whether n is square free or not. So it basically counts the number of natural numbers which are square free. And then Bn, you can see that it converges in distribution to Bernoulli 6 by pi square. This 6 by pi square is actually 1 by zeta of 2. So since we are dealing with square free, it is zeta of 2. If we are dealing with kth power frees, it would have been 1 by zeta of k. And we can also discuss the valuation at a prime p. So this Vpn basically represents what is the largest power of p that divides n. And it is 0 if p does not divide n. Then this Vpn converges in distribution to geometric 1 by p. So you can see there are lots of examples, and there is this famous Ardo-Skag theorem that basically popularized the subject of probabilistic number theory, which is if you let omega n denote the number of prime factors of n, and define capital Xn as omega n minus log n divided by log n. So this log comes because omega n, it actually it is like if you calculate the asymptotic order, it is log n, and this division is something like its standard deviation asymptotically. So you are taking a random variable, you are subtracting its expectation and dividing by this is actually the square root of the variance, and you expect it to behave normally, and it indeed becomes a standard normal random variable. So this is the famous Ardo-Skag theorem. But these are like some classical examples. We are working with classical arithmetic functions and dealing with their probabilities. That is how probabilistic number theory started. But soon we will see what happens. So our next topic would be to analyze how like the properties of Riemann Zeta function through some probabilistic arguments. So first of all, why like sudden change from classical arithmetic functions to the zeta function? So let us see how zeta function came into study in number theory itself. So Euler, he studied zeta function as a function of natural numbers. So when you look at this series, so for one, this series does not converge. For other natural number, this series converges. And Euler also proved that it is given by this infinite product. And he proved that zeta of 2k, which are the even integers, is given by this formula. These b2k's are the Bernoulli numbers. So Riemann, in 1857, his famous memoir, he revolutionized number theory by saying that instead of looking at natural numbers, if I look at complex numbers, then what happens? So if my s, its real part of s is greater than 1, then the series defining zeta s converges absolutely and uniformly. For real part of s less than equal to 1, the series diverges. So there is this abscissa of convergence, which is like vertical line passing through 1. To the right of it, the series converges absolutely and uniformly, and to the left and on the line itself, the series diverges. But even though the series diverges, Riemann found a meromorphic continuation with simple pole and blah blah blah. So for those who are not familiar with complex analysis, this means that he found some other function defined on the whole of complex numbers except this point at 1, such that the zeta function is analytic on that except one entire complex plane, and close enough to 1, it behaves like 1 over s minus 1. And there is a theorem in complex analysis that says that if you can find such an expression, it has to be unique. So this is the only possible way of defining zeta in the other part. And he also proved this famous functional equation, which is not a symmetry of zeta, but after multiplying zeta with this gamma factor, it has a symmetry about half. So you can see this like it's like a reflection through half. And the reason why it is so important to number theory is because there is a connection between zeros of zeta s and the distribution of prime numbers. So as you can see that the zeta function is product over some function over the primes, but there is a theorem in complex analysis, which is the Weierstrass factorization theorem, which states that certain complex analytic functions, they are also product of some function over their zeros. So on one hand, it is the product over some function over the primes. On the other hand, it is also a product of some function over the zeros. So if you take the logarithm and take a derivative, which is what Riemann did, he showed that there is some connection between these two, a very important connection. So to study prime numbers, you can study the zeros of zeta function and also the converse. And then he argued something else, that from by this looking at this Euler product, you can say that because this is valid only in real part of s greater than 1, that there are no zeros of zeta function in this region, real part of s greater than 1. And by the functional equation, if you take the gamma factors to the other side, then you can say that the zeros of real part of s less than 0, they are at, these actually come from the where gamma function goes to infinity, which is at -2, -4, and so on. It also goes to infinity at 0, but there is this other gamma factor which cancels it. So there are no zeros in real part of s greater than 1, and the only zeros in real part of s less than 0, which are the trivial zeros, are like this. So it is completely studied, completely specified. But there is an intermediate strip which is between 0 and 1. So the question remains that what happens in this mysterious critical strip 0 less than equal to real part of s less than equal to 1. So this is called the critical strip because you need to study the zeros there. It is of critical importance. And there were some speculations by Riemann. He was not able to prove them, but he speculated two things. That first of all, there is no zero on real part of s equal to 1. So uh, to the right of this, there are no zeros. That is trivial, but there are no zeros on the line itself. And if you just assume this, you can prove the classical prime number theorem. So the fact that there are actually no zeros, it was proved independently by Jacques Hadamard and Delavalli Poissy, and they also proved the prime number theorem using this. But if you look at the classical version of the prime number theorem, the error term, so if you write pi x equal to x by log x plus some error term, that is like marginally smaller than this, so it is not a very good asymptotic result. You would ideally want a better approximation to study prime numbers in a better way, and that lowering of the error term is not possible unless you prove a stronger zero free region. And this was also speculated by Riemann, that you can come like narrow it the zero free region to the line, it's to the line half line itself. Like there are no 0 on 1, there is no 0 up to half. And this is the famous Riemann hypothesis. This is still remains open, and this is one of the 7 Millennium Prize problems. So it is like one of the most famous problems. And before proceeding on to the probabilistic aspects, I want to make two remarks. So Riemann zeta function is an example of a large class of functions which are called L functions. And just like Riemann zeta function encodes the distribution of primes, these L functions, they encode certain other arithmetic information. And they all satisfy similar properties. It is given by products, there is functional equation, monomorphic continuation, knows like the critical strip where you need ideally need to know what the zeros are and how it behaves. So Riemann zeta function, the study of L function started where zeta function was taken to be a prototype. And okay, that was the first point. And second point is that when Riemann continued from natural numbers to complex numbers, he was working with the Euclidean or the Archimedean metric, but it can also be continued to CP analytic spaces where CP are like p-adic complex numbers. So just like the Archimedean world, for every prime p, there is a non-Archimedean world where everything behaves differently, but similarly also. And studying the CP analytic spaces is as important as studying C, and zeta s can also be continued to CP because these Bernoulli numbers B to K, which are the arithmetic part of the special values, they satisfy certain continuity properties. So with those two remarks, now let's move on to the probabilistic aspects. That studying the zeta function in the critical strip is of fundamental importance. So how are the values of zeta s distributed? So now we will change our probability space. Now the probability space omega t, this is the closed interval minus t to t, and we are taking the Borel sigma algebra, and the measure is the uniform measure, which gives the measure to an open interval ab by b minus a divided by 2t. So this is like the uniform probability measure, and by this you can extend to all Borel sets using Kerr-Theodori extension theorem and so on and so forth. So this is the probability space, and there is this theorem by Bort-Jessen. He proved that if tau is greater than half, and you define this random variable z tau t from omega t to complex number by t going to zeta of tau plus it. So tau is like the point between half, not between half, like it's right to the right of half, and this t, it actually represents vertical movement. So you are looking at vertical translates of zeta tau. Zeta tau is on the real line, and you are looking at how it behaves on the vertical line. So fix the line at tau, the vertical line, and with this t you are moving along the vertical line up to this ends minus t and minus capital T and minus capital T and capital T. You are oscillating the zeta function between those two ends, and you are looking at how does it behave. So he showed that there is a probability measure on C such that Z tau t converges in distribution to this mu tau. And also the support of mu tau is compact if tau is greater than 1, and the support is equal to the whole of C if tau is between half and 1. So the support is compact if tau is greater than 1 is not very difficult to prove, because there is an upper bound, like zeta of tau plus it can be, like modulus of that is always less than equal to zeta of tau. But it is very interesting that the support is whole of complex number if tau is greater than half. But this result is still not very much, because it is a pointwise approximation result. The next result is much stronger. It is like a uniform approximation result. So let D be a compact subset of complex numbers, and you can define HD. This is the set of functions from D to C which are holomorphic on the interior and continuous on D. So holomorphic means basically complex analog of differentiable. So you can think of them being like differentiable in the inside of D. D is a compact subset of complex numbers, and my F, it is differentiable inside D and continuous. Well, you can just assume continuous on the boundary. By the differentiability condition, it is continuous on whole of D. And there is HD star, which is the functions in HD which do not vanish anywhere on D. So if you think HD as a ring, then this is the group of units. And there is this theorem, which is Voronin's universality theorem. You can see that it came much after Borjeson. So you are specifying this D, which lies completely between the critical line and the line of convergence. So there is this line passing through half, there is this line passing through 1, and the D, it is completely between those two lines, and it is compact. So now if you take any F inside HD star, means it is in an HD and it does not vanish, and you take any epsilon, then there exists some T such that zeta s and fs are very close, epsilon close by epsilon amount in the L infinity norm. So which is very surprising that given a compact subset D, this HD star can be like a very large class of functions you can think of. Like basically any function which is holomorphic on D, and like holomorphic on D's interior and continuous on D, which is like large class. And surprisingly, if you look at just the zeta function of that D and you translate it sufficiently large amount vertically, you will see that the translate of the zeta function approximates the F uniformly. Like the supremum is less than epsilon. But this is still not that interesting, because this just gives the support of zeta function. On the other hand, there is Bagchi's theorem, which also specifies how the zeta is distributed. So Bagchi was a student of Indian Statistical Institute, Kolkata, and this was in his PhD thesis in 1981. So he tried to argue probabilistically why such a universality theorem should hold. So now ZDT is a random variable from omega t was earlier, this omega t, to HD, and HD is like a functional space. So this is actually a functional limit theorem. So ZDT is defined, so ZDT at t, so at a specific t, it has to be a function in HD. So we have to specify what it does to a complex number S. A complex number S is taken to zeta of S plus IT. So now instead of looking at a point and moving it vertically, you are looking at a compact subset D, how zeta is distributed in that compact subset D, and you are moving the entire subset up or down depending on the T. So there is no randomness in S. The D is also fixed. S going to zeta S is like a fixed function, but depending on T, you are translating the function up or down. So that gives you like a random function in HT. And so again, this is parameterized by t. So z dt, if you look at how it behaves as t goes to infinity, you would see that z dt converges in distribution to zd, where zd is also given by an infinite product. And the xp's are the random variables. Xp's are IID uniform S1. S1 means complex numbers with modulus 1, the unit circle. So these xp's, they are like rotation vectors because they're in the unit circle. They are rotation vectors, and so like if you think about just zeta function, there is no xp present here. They are like p power minus s, but this zd is like the p power minus s factors are rotated like randomly. They are IID uniform S1. So there is no rule governing how it should be rotated. It's just random. So this is the remarkable functional theorem proved by Bagchi, and from this you can compute the random like support of the random variable zd, and indeed the support of the limit random variable is equal to ht star union with the empty set, like not empty set, union with constant zero function. So from this theorem, you can derive both Borjeson and Voronin. So to derive Borjeson, you have to compose both sides of this convergence distribution by evaluation map at a fixed point. So if you evaluate ZDT at a fixed point, if you evaluate ZD at a fixed point, you will get this convergence result. And you know that if you compose, like if somewhere random variable converges in distribution and you compose it by a continuous function, that also converges in distribution. So this evaluation map is continuous under the L infinity norm. So Borjeson can be derived, and Voronin can also be derived because it says that the support of the random variable zd is ht star. So you can take a large enough t such that this epsilon approximation holds. And next we can give some idea about the proof, how Bagchi's theorem is proved. So for Bagchi's theorem, the d is between half and 1, but heuristically suppose it was situated to the right of 1, then zeta is given by this infinite product, and there are two components here, this s which is deterministic, and then there is this t which is random. Like the stochasticity comes from t. So you can look at the asymptotic behavior of p power minus it, the sequence indexed by p. And there is this theorem that if you look at these random variables, which are just the p power minus it, the infinite sequence, and you let the t go to infinity, then xt converges to x, where x is like a vector of IID uniform S1s. So p power minus it, they are rotation vectors, and the fact that each of them is a uniform S1 is not very surprising because equal arcs get equal amount of length. This t is moving linearly, so equal arcs get equal lengths, but it is slightly more difficult to derive that they're actually IID, like they're all independent also. That is a bit tricky part. Now, with this result, if you try to prove Bagchi's theorem for real part of s greater than 1, it is 2-3 lines. You just have to show that a certain function is continuous. Then you apply that continuous function to both sides. That will give you the Bagchi's theorem in real part of s greater than 1. Between half and 1, some more work needs to be done. So let us fix a sequence of IID uniform S1s indexed by primes, and define xn to be equal to product over p divides n, xp to the power of vpn. So xp's are like these xp's are these random variables, and vpn, if you remember the definition we gave earlier, it is like valuation at n. So this denotes the largest power of p that divides n. So this is there. And but now the xn are neither identically distributed nor are they independent, right? Because let's say x4 is just x2 square, so there is no independence, and it will not also not be same distributed as x2. And now zs, you can define it as the limit random variable, which is 1 minus xp p power minus s inverse the product over all primes. And if you formally compute the product, this will be actually be equal to summation x and n power minus s. This works by the because xp is completely multiplicative. So the similar way how y zeta s is equal to the infinite product and why this sum is equal to this product, they go by the same proof. uh, Essential argument is that xp is completely like xn is completely multiplicative by this definition. And so this defines an infinite random sum, and this defines an infinite random product. And you can look at d. So uh, you can define these random variables zd and zd tilde from d to c. So zd is s going to the product, and zd tilde is s going to the sum. They are both hd valued random variables. So this is the result, that they are actually both hd valued random variables. So without the xp, deterministically it diverges, but due to the rotation in xp, the series and sum, and like the series and the product converge almost surely. And not only that, the two things are also equal almost surely. So instead of looking at the product, you can look at the sum. You can, instead of looking at the sum, you can look at the product, depending on which one is more useful. This is the first result. The next result is that if you fix phi, which is like a smooth function with compact support, it takes 0 closed 0 open infinity to closed 0 comma 1. So the phi function will look like, well, ideally it should look like you are starting from 1, you are decreasing monotonically to 0, and you are actually achieving 0 and then continuing, like it's continuously 0 from that point onwards. So it's not like normal density, which is asymptotically going to 0. It's like hitting exactly 0 and 0 from that point onwards, something like that, because of the compact support. And you're also assuming it is smooth. So necessarily, like, obviously there are lots of function phi available. You can pick any such function phi. And for this side and the next slide, you can let d, like you can fix d. So instead of like keeping d in the notation, you can just remove d. Like there is some d which is fixed, and you remove d from the notation, otherwise it will look a bit clumsy. So zd, we are going to call it as z, and zdt, we are going to call it as zt. So basically just removing the d from the notation. Then there is this theorem, which is the tricky part. So So now you define two random variables zn and znt, which are ideally similar to these two. So Zn is S going to Xn phi of S small n divided by capital N, n power minus S. So this is actually a finite sum because phi has compact support. So let's say phi becomes 0 after some alpha. So for natural numbers n which are greater than n alpha, this phi is actually 0. So this is not an infinite sum, this is actually a finite sum. And this is like a truncation. So when you're dealing with probability and convergence, a common trick to use is truncation. But since we are dealing with some analytic functions and stuff, the truncation has to be done in a smooth way. This phi, it's actually what it does is that it truncates it in a very smooth manner. So this is like a truncated partial sum in a smooth manner, and Znt is defined similarly. This is phi of n by capital N, n power minus s minus it. So this is like the smoothened part of the limit random variable. This is the smoothened part of the, like before taking the limit, the zdt. And you have to also be careful because we are not working in the region of convergence, so z is not given by the sum, but the argument is that it will still, even though z is not given by the sum, znt, the smooth partial sums, will actually um, approximate it, but yeah, there will be an additional price to pay. So with Zn and Znt defined this way, there exists some delta greater than 0 such that the expectation of the norm z minus zn is this sign symbol means less than equal to some constant times n power minus delta, means it goes to 0, as in capital N goes to infinity. And also expectation of the norm zt minus znt is less than n power minus delta, but there is an additional price to pay, which, so you cannot take very n to be very large here. There is also an n in the numerator, but fortunately there is a t in the denominator, and we will see that this t in the denominator is actually very important. So the reason this term comes up, because you can, first of all, you can always expect, because z is not given by the series here, so there will definitely be a larger error term. But there is also an important thing, which is the pole of zeta is at 1, which we mentioned. So when you are, so okay, let me just tell the idea of the proof. The idea is to take Mellin transform and the Mellin inversion. Now Mellin transform is a like integral transform, which is why it requires this smooth function. So since it is an integral, it will behave nicely if you pass it a smooth function to it. And then the next step is to use Cauchy's theorem in complex analysis. So you will move the vertical line to the right of the convergence line, that is allowed by Cauchy's theorem. But since you are crossing this pole at 1, there is another extra term to incorporate here, which will come from that pole. So there is one point where zeta s does not behave nicely, which is at 1, and you are crossing that line. So as long as you do not cross that line, it is fine. But once you cross that line, there would be another term which you have to incorporate, another error term, which is this term. And so we have these nice results that Zn approximate Z and Znt approximate Zt. And there is also another thing which is easy to observe, that Znt also approximate Zn. Like these approximations are on n, like basically on n. So if you let n go to infinity here, this goes to 0, and you cannot let n go to infinity here, but still there is a nice term which gets lower if you take very large n. And this convergence is on t. So if you let t go to infinity, you know that how this n power minus it will behave, that is by this theorem. So there is p power minus it, and if you take some products, you will get for n power minus it also. You would know that they converge to the capital Xn, and this is actually a finite sum. So when you have this n power I minus its, you make a finite sum, then that is actually a continuous function of the n power minus its. So if n power minus itis converges to this xn, and you are taking the finite sum, which is basically a composition by a continuous function, then znt, this random variable, also converges to zn. So there, everything is very closely approximated, and now some analysis needs to be done, some final analysis, which is all about epsilons and deltas. So before that, I would like to recall some theorem about convergence in distribution, which says that if you want to prove that zt converges in distribution to z, you can show that for any bounded Lipschitz function, the expectation of f of zt minus fz, this goes to 0 as t goes to infinity. So that is one trick way to show the convergence in distribution. One is to go directly by the definition. Another is to show that something converges and then realize this as a continuous transform to the previous convergence. And this is the third way to do it, which is by showing that the expectation of any bounded Lipschitz function is like it goes to 0. So now there is the standard trick. You have this mod of expectation, and now we are going to use triangle inequality. We are going to approximate zt by znt. We are going to approximate znt by zn, and we are going to approximate zn by z. So from zt to z, there are 3 intermediate steps. One comes at znt, one comes at zn. So there are 3 things that need to be taken care of now. And Next thing is you're going to use triangle inequality again. So this mod, you can take it inside the expectation, and since this is a Lipschitz function, mod of f of zt minus f of znt, that will be less than equal to some constant times the norm of z minus zn infinity. So this is the norm on hd that we're working with, and that constant what was there, it comes out of the expectation, and we'll use this notation less than. So we are going to leave the second term as it is, and again do the same thing for the third term. So we have again taken the mod inside using triangle inequality and use the Lipschitz property. Now by the previous result, this will be less than n power minus delta, and sorry, there are two plus here, that's a typing mistake. The second term we are keeping it as it is, and this term there is n power minus delta plus an n by t. So uh, like we can fix large, like fix n large enough such that this n power minus delta, this is less than epsilon by 4. So epsilon is fixed before the argument. We can take a n large enough such that this n power minus delta is less than epsilon by 4. Same for this, and the remaining thing remains as it is. So we are not exactly letting n go to infinity, we are fixing some n which is large enough for our purpose. And now we have that znt converges to in distribution to zn. So again, that was an both side property. So if znt converges in distribution to zn, the expectation of f of znt minus f of zn, that will goes to 0 as t goes to infinity. So we are while arguing this, we are trying to prove that the expectation goes to 0, which is why there is convergence in distribution, but that result holds in the other direction also. Since there is a convergence in distribution, this expectation goes to 0, and there is an n by t term here. If t goes to infinity, this will also go to 0. So we can choose t large enough such that this is less than epsilon by 4, this is also less than epsilon by 4. So together everything is less than epsilon. Epsilon was arbitrary, so this expectation goes to 0, and we have indeed proved Bagchi's theorem. So before moving on to the next topic, there are some key steps in the proof that I would like to recall. So first step is this behavior of prime numbers. Well, you can actually see that it is actually related previous also. We saw that division modulo primes are independent, and in some sense they are uniform. So in the same case, rotation by primes, that is also independent and uniform. So this is like one of the key arithmetic steps that is required in the proof. And fortunate thing about this is that instead of working with zeta function, if you are working with some other L function, this product will not be the same, but it would only involve these p power things. So this part of the argument is already generalized to every L function. There is nothing you need to think about differently in those cases, right? And then this is okay. The next part of the argument was here. So as I mentioned earlier also, zt is not given by the sum, but the smooth partial sum still approximates znt. This happens only in the case of zeta function. Generally, it uses a property of zeta function which is called the mean value property, not to be confused with the like derivatives mean value theorem, Lagrange's mean value theorem, not that one. Mean value property satisfied by zeta function only, and that is in general not satisfied by all L functions, but still there are generalizations to various cases for which it can be done. So this is like the second crucial thing that is used in the argument, and rest of the things are fine. So we have Bagchi's theorem, which is this. From there, if you compute the support of the limit random variable, you will see that this is equal to ht star. So this provides a remarkable proof, like alternate proof of Vernon's universality theorem, completely through a different light by seeing in terms of probability and distributions and functional limit theorem. So this is like this gives more intuition why it shows such a thing. But but there is still one remaining that so far in this discussion we have never talked about what happens on the critical line itself. Now ideally if you assume the Riemann hypothesis, then like in the critical step actually only thing that matters is the critical line itself. So apart from the critical line under Riemann hypothesis there are no zeros there, so there is supposed to be nothing interesting going on in this part of the arguments, and the only critical line is very important. So we would like to know next that what happens on the critical line itself, not here and there outside of that, like on the other sides of the critical line. So actually the problem is that zeta function, just like other L functions, this behaves very much unpredictably on the critical line itself. So you can see that apart from the critical line, it still behaves wildly. It goes like it approximates any holomorphic function uniformly, but still there is a limit theorem. Unfortunately, in the critical line, there is no limit theorem itself. Like the values of zeta s, they do not take a limit random variable, but if you take the log of zeta s, we would soon see that it is actually a nice like what to say, a very nice distribution. So if you look at this limit distribution, it is something very non-generic. Well, people working with probability have probably never seen this kind of a distribution. This is very non-generic, not like the well-known distributions. On the other hand, in the critical line itself, we are faced with a very well-known distribution, a very well-known distribution actually, and this is the distribution that people like the most. So if you take LT from omega t to R and define LT by 0 if zeta is 0, and the log of modulus of zeta it otherwise, then this LT normalized by its variance also converges in distribution to normal 0, 1. Since this reminds us of central limit theorem, this is called Selberg's central limit theorem. It was proved way earlier before Bagchi, but at that time these functional things were not known, and unfortunately the functional results fails to hold if you look on the critical line. It has to be on either side of it. So this is like, this sheds more light to the fact that why the Riemann hypothesis might be true, because if we're looking outside of the critical line, there is some sort of a limiting behavior, and if you're looking on the critical line, there is a completely different limiting behavior, which shows that there is something special about the critical line, which is why all the zeros lie there and not on the other sides. This is the famous celebrated Selberg central limit theorem. He also proved as a consequence to this that at least 40% of the zeros of Riemann zeta function, like asymptotically, they lie on the critical line. So if you look in a rectangle, how many zeros lie? And if you look at just like rectangle up to height t, and on the other side, if you look at the central line up to height t, how many zeros are there? If you take the ratio, then it is asymptotically at least 40%. And Selberg used to claim that I have proved 40% of the Riemann hypothesis, so I should get 40% of the prize. There is also another important thing, that if you remember Borde-Jessen, you saw that the support of mu t is compact if tau greater than 1, and it is equal to c if half is less than tau less than equal to 1. So you still do not know what happens at tau equal to half, and this came far later. This was due to Emanuel Kowalski in 2012, which is like very recent compared to the other things. It's proved recently that the set of zeta values in the half line, that is also a dense subset of C. So if you take the support, which is like the closure of this, it is also C. So as you can see, the results in the critical line are far more difficult, and there are a lot less generalizations to other L functions and things. Now, once people have this kind of a result, the next thing they ask is what happens to the moments of the zeta function, and there are also very celebrated moment conjectures about zeta functions, which are due to Keating and Sneth, and some of them are proved by K. Soundarajan, which, like, if you blindly believe that log zeta s is a log zeta s is a normal random variable with this variance, then you can estimate what its variance, like what its moments are. and so ideally the moments of zeta s should be somewhat similar, and that is the conjecture. But there is a constant term there which is comes from some motivations from random matrix theory. And there is also another line of research where people look at the maximum of zeta function. So if you look at a window of width 1 and you move at that you move that window throughout the critical line, and you look what happens in like the maximum of zeta s in that, like maximum of the modulus of zeta s in that window, then how does that maximum behave? And that is even more non-generic than the behavior of zeta function itself. It is related to Brownian motions and other stuff. So those are like very recent advances in this theory which I studied. So this is actually not Selberg's central limit theorem. This was like Selberg proved it without the mod, and without the mod, this is a complex variable. So to take the logarithm, you have to actually define it appropriately, like picking an appropriate branch of the complex logarithm. If you do that without the modulus, like if you want to know the rotation also, then that is also true. And in turn, like you have to define the branch appropriately. Then this LT, by this same normalization, this will converge in distribution to the complex normal distribution, like complex standard normal, which is basically like take two independent normal random variables z and like z1 and z2, and look at z1 plus I z2, that is the complex normal random variable. So without the mod, this is like that complex normal random variable. And so here are some references. First one is of course the PhD thesis of Bagchi. This is in the Indian Statistical Institute library, like the online website, but I think the website is making some problems now, so you won't be able to find it. And there is this book by Emanuel Kowalski, An Introduction to Probabilistic Number Theory. The method of the proofs here actually that are present in the slide are actually taken from this book and not the thesis. It used more complicated stuff. So this is like a simpler one. And you can also look at the distribution on the critical line. This is a paper. Uh, so that's it. Does anybody have any questions?
Yeah, can you go to the slide on the universality theorem?
Okay, sure. Yeah.
Yeah, so like I'm trying to understand, like like is this theorem like say something really is special about the zeta function, or is some
Yeah,
version
so
of this true for like all meromorphic
no,
holomorphic?
this is not true. So if you know, yeah, of course, you know Picard's theorem, which states that if you look at the values of complex analytic, the range of a complex analytic function, that can miss at most 1 point. So it is not surprising if you look at the whole plane, but there is this one line, this support of zetas is like a dense subset of that line itself. Not on the entire complex plane. If you just look at one single line, it is still dense. So this is way more stronger, like not about just meromorphic functions only. And f has to be holomorphic here. F cannot be meromorphic. And f cannot be zero also nowhere. So no zeros, no poles inside D for this f.
Yeah, thanks.
Okay. Uh, Anybody else? So that's it then. Thank you everybody for attending.